So let's revise what we have done so far. So first of all, we created a Spark config object with the local star, which means that we will be having four number of threads, worker threads for this Spark config. And because I've got 4 CPU cores in my laptop. And then we created data of 1 billion size, having random values 100 to 147 something. And then we have the benchmark test. We will be passing this RDD, and we will do a reduce operation by calculating the sum, and then we'll do the benchmark. The main idea of this benchmark test is that how much time it takes for a particular operation after we increase the partitions or decrease the partition using repartition method. Then we have our test case here. So first of all, we will print that what is the default minimum partition, because as mentioned that although we have using 4 worker threads, but maybe the data based on the data size can be it can be very small or very big. It will do the. But here in this case, because I'm using local, the default minimum partition should be around like 2, I think, and default parallelism would be still 4 because I am using local star here and I got 4 CPU cores. So the default parallelism before we do any operation, it would be 4 number of threads. Then we create our RDD here by using parallelize method, and I'm explicitly passing 14 here, which is the number of slices or the number of partitions that would be created. So instead of using the default multi-partitions of 2, I override it with 14. And then if I don't specify it, then based on the data size, it's like 64 MB of like allowed in HDFS file system. So if it is like more than 64 MB, accordingly, that number of slices will be created. But because of explicitly creating this number of slices to 14, it will create this RDD with 14 partitions. And then once we run this benchmark test, I have given this get number of partitions in our final result. So it means that we have got 14. It will be printing for 14 partitions, that how much time it took. And then we increase the partition from 14 to 28. And we expect that the performance would be degraded here because it's like extra cost for creating those partitions, those empty partitions, I would say. And this will definitely have a cost. And then we reduce it from 14 to 7. We expect that this would be better than 14, but maybe it can be also similar to 14. So let's run this and see whether our assumption is correct. I click on run button here. It's running now. So we can see default mail price is 2, default price is 4 as expected. And now he's just doing the sum of those random numbers that we created, 1 million. So sum is coming out to be this. But more important thing is that we have to see what is the. Okay, so for 14 partitions, for the first benchmark run, numbers like 14, it took around 1.6 seconds. And now it is running for, you can see there's a delay here because it is trying to create this repartition of 28. So I expect that this would be much bigger than 1.6 because it's 28. As you can see, it's 2096 now, more than 2 seconds now with partition of 28. Now we have got 7. I think 7 would be almost equivalent to 14 or slightly better than that. Okay, so let's analyze this. So default minimum partition is 2, default parallelism is 4, and then we have got 1.682 seconds for 14 partitions, default number of slices for 14. And then for the second benchmark test for partition 28, it increased to 2096 for 28 partitions. And for 7, when we reduce it, is the best performance because we have reduced the number of partitions. That's why I said that, because even for 14, a lot of partitions would be empty because the data is not that huge. That's why reducing it to 7, and then after doing because repartition will cause it will reshuffle all the data, and after doing the reshuffling, after that when we call this reduce method in our benchmark test, it's the less number of partitions which are taken care of for doing this operation for sum. That's why the performance is better. So this is all about repartition, and in the next video we will do the same thing for coalesce method. We should always use coalesce method because it's whenever we are reducing the partitions, because it has got a better optimization in the API, and we should always use that. So see you all in the next video for coalesce method.